Okay, today we're going to talk about temperature. Okay, we all have a general idea of what temperature is. You hear the newscasters talk about it every day in the forecast. But scientifically, temperature is the measure of the average kinetic energy of the particles. Okay, it's not exactly the average kinetic energy, otherwise we would measure it in joules, but it's the measure of the average kinetic energy of all the particles. The faster the particles are moving, the higher the temperature, and vice versa. That leads us to the kinetic theory of matter, which is what I just said, okay? The faster the particles are moving, the higher the temperature. The slower the particles are moving, the lower the temperature, okay? How do you change temperature, okay? Well, temperature can be changed by adding or removing heat, okay? Now, a lot of times we use the word heat and hot and all of that, and we think temperature at the same time. But heat is actually measured in joules. It's an energy, okay? And if you add energy to the system, you're going to increase the kinetic energy of the system, and the temperature is going to rise. So let's just look at an example here. Okay, I've got a container. Inside that container, there's some water and an ice cube, okay? So what's going to happen? Well, the water, say it's at a warm temperature, okay? So what's going to happen is this. Heat is going to flow from hot to cold, okay? So heat is going to leave the water and enter the ice cube, okay? And as that happens, heat's leaving the water, therefore the temperature of the water is going to go down. And also, heat is entering the ice cube, so the temperature of the ice cube will become lower. Okay, so heat is flowing from hot to cold, which leads us to when is this going to stop? Okay, heat flows from hot to cold. Well, when will it stop? That heat is going to stop flowing when the objects enter thermal equilibrium. Okay. Thermal equilibrium means they're the same temperature. Equilibrium. Okay, they are equal. So they have the same temperature. That's when heat is going to stop flowing, which then leads us to the 0th law of thermodynamics. Okay, this says that if Object A has the same temperature as Object B, and Object B has the same temperature as Object C, then Object A and C have the same temperature. Okay, it's a transitive property. Okay, if two objects have the same temperature as a third object, then those two objects also have the same temperature. Okay, something to notice about temperature is a scalar. Okay, now you're going to notice that we do sometimes have negative temperatures depending on which scale we're using. Okay, it doesn't tell us the direction of the temperature. It just so happens that it goes into the negatives for some of these scales. Okay, so let's look at some of the history of the various scales. We're going to start with what we use here in the USA, Fahrenheit. Okay, well, Fahrenheit was developed by Fahrenheit. Okay, and what he did was he took a solution, okay, and he made it as cold as he possibly could, okay, and when he did that, he called that temperature 0, okay, it was the coldest temperature that he could make, and then he said, all right, well, if that's the coldest temperature that I can make, then I'm going to go ahead and define another temperature for body temperature, and I'm going to say that is 96. Okay, so 0 was the coldest he could get, and then he said body temperature 96. We're not sure why he said body temperature 96. We're going to go ahead and say a lot of people think it's because it's divisible by a lot of numbers. Okay, and you might be thinking body temperature is not 96. Well, what happened is after he started this, he came to realize that the freezing temperature was pretty close to 32 degrees Fahrenheit, but not exact. And he said, you know what, freezing should be a nice round number. So he said, I'm going to change this, and I'm just going to say 32 is freezing. Okay, and then he also noticed that water boiled, okay, around 212 degrees Fahrenheit. Okay, but it wasn't exact. It had decimal places, and he decided he didn't want to have decimal places for the freezing and the boiling points. So he defined them, which skewed these numbers a little bit. Okay, that's a little history of Fahrenheit. Fahrenheit became popular because he used mercury, and it does a nice job of expanding and contracting through a large range of temperatures. Okay, so it made a very good thermometer. All right. Next up, let's talk about Celsius. Okay, so Celsius comes along and he says, you know what? I think this should be more like the metric system. Okay, but going from 0 for freezing to 10 for boiling just isn't a very large scale. So instead, he made 0 freezing still, okay, but he made 100 the boiling point, okay? And now we use both of these, and we need a way to get back and forth between the two. So one way to do this is to just go ahead and create a line of best fit, okay? So think of these as being points. All right, so let's make some points. So we're going to make the point 0, 32, and another point 100, 212, okay? And then we're just going to simply find the line of best fit for this. So we're going to take the change in y, so 212 minus 32 over 100 minus 0. And I get 180 over 100. That reduces to 18 over 10, which also then reduces to 9/5. So that is our slope. And then we need our y-intercept, and we could go ahead and substitute and solve. But if we look right here, okay, we're at x is 0, that's the y-axis, so this is our y-intercept. So we have our y equals 9/5 x plus 32. And now we just need to decide, well, the y-axis, that was the Fahrenheit. So Fahrenheit, temperature in Fahrenheit, is equal to 9/5. This is the temperature in Celsius, plus 32. And if we look back, that is our equation that we will use, okay? And then the next one that came along was Kelvin. And Kelvin said, okay, if temperature is the average kinetic energy of the particles, kinetic energy means you have to be moving, okay? So at some point, if you keep lowering the temperature, they're going to move slower and slower and slower, and there's got to be some point when they stop. And he defined that to be the 0 point, okay? And so basically you just take your degrees Celsius, and he said, okay, well, negative 273 degrees Celsius is when they would stop. So therefore, if I'm just going to make it so 0 is the smallest number, I add 273 to everything. And that is what Kelvin did.